And where here we have yet another problem to solve. And the statement of the problem is two cubes of same mass are attached to the ends of an inextensible weightless thread. You can see the picture. Passed through a hole in a horizontal table. This hole in a horizontal table creates many problems. I know. This is one way. This is going to be difficult problems to solve. If even you can solve it, it is still hard to get the accurate solution. The upper cube slides along the plane along a circular trajectory with an angular velocity omega, and such that the lower cube is motionless. Okay, lower cube is in equilibrium. There is no friction, and if you I slightly tug the lower cube in the vertical direction, that means vertically downward direction, a small oscillations will occur. Find their frequency. Oh, so without doing anything else, you would know that if this thing is motionless, then forces acting on it is mg and tension in the string, and this tension also acts on this, and this is moving in a circular path. So this tension creates the angular acceleration equal to omega square L, and m omega square acceleration is omega. This tension will be equal to m omega square L, and this will be equal to mg. So we can write here, you can get the distance of the upper cube from the hole during equilibrium sliding. This will be equal to L equals g by omega square, and there is no problem till now. Now let's increase this distance L. After the lower cube is pulled down, and at some point reaches, that is the maximum value. That means just pull down it by a distance delta x, so that this delta x length is very much smaller than L, and the velocity of upper cube is changed now. Its velocity has become something else. I don't know what its velocity is, but its velocity is certainly not okay. It is moving in a circle, but its velocity is not. Velocity is definitely not equal to omega anymore. But during this pulling we pull the string, one thing was clear: the angular momentum of the upper cube remains conserved in this process, because the force which is used in pulling the upper cube is passing through its axis of rotation, and it is going to create no torque about the axis of rotation. So its angular momentum is going to remain conserved. And of course, since there is frictionless everywhere, so mechanical and energy conservation is also there. But if it has initial angular velocity omega, so that its linear velocity was omega L, and it had changed now to v dash, and the length has become something L minus delta x or L plus delta x? What should I take? I pull this block in this direction or should I pull this block in this direction? I would go with it. Yeah, it's fun. I always did the problem by pulling this block. No, I'm in the mood to pull this block in this direction. So the length of its radius of its circular motion I changed to L plus delta x. For the I'm talking about the upper block. So I would like to write the principle of conservation of angular momentum for the upper block during its pulling on the pulling to the right, and I would like to write it angular momentum was initially m omega l mvr equals m v dash, its velocity now become v dash and length now become L plus delta x. So this is my equation number 2, because this was equation number 1. And what about the total mechanical energy of both the cubes, because they remains conserved? I have observed this thing, so I would like to write the total mechanical energy at this moment. That will be the kinetic energy. It will have a kinetic energy, and the block has reached to this position and it is motionless. This lower block is motionless, so I can write here its kinetic energy as it is not moving anymore. It has reached to its equilibrium, its extreme position. The delta x is some extreme position of this from this equilibrium position. So at this position its velocity is equal to 0, its kinetic energy is 0. So the total mechanical energy of the system at this moment becomes half m v dash square plus its gravitational potential energy has increased by delta x. So this can be written as mg delta x. And well, this is the total mechanical energy of the system at this moment, and we can find the value of v dash from here and put here, and this will be scary. That will be half. No, leave that half. I'm going to write something v dash square first, and v dash square is m omega L by L plus delta x square by 2 plus mg delta x. This is its total mechanical energy at this moment. Well, this is my equation 3, and of course potential energy was measured from this position, from the equilibrium position. Data was taken at the equilibrium position. Now I would like to use the mechanical energy conservation. So its mechanical energy, I would like to write this mechanical energy at the moment of passing the equilibrium position. And what was it? That means I would like to write the energy of both cubes at the moment of passing the equilibrium position. And at the moment of passing the equilibrium position, that means this position, that means this position, both will have some velocities. Let's call this velocity v, and it was also rotating So I can write, let's call this velocity v. Both must have been passing with a speed v. So I'm going to write this total mechanical energy simply by half m omega L was the velocity of upper block, half m omega L square, half m v square, plus both were moving when passing through equilibrium position with the speed v. We don't know anything about it, so it will be both. That means we need to multiply it by 2, so half mv square. This is my equation number 4. So that means we need to write down the equation of conservation of mechanical energy, and that will be simply equal to E1 equals E2. So m will get cancelled out, and this will become simply 2v square. So I'm going to write 2v square, m will get as cancelled out, and this half 2 will half. So I can put it to here. I think this equation can be written as 2v square omega square L square equals omega square L raised to 4 divided by L plus delta x square plus 2g delta x. This is one equation we will get from mechanical energy conservation, and remove this, the burden of being an equation. This is equation number 3 simply. This is the principle of conservation of mechanical energy equation. But we need to work on something, that is delta x is very much smaller than L. That means the fraction delta x by L is very much less than 1. But how much? The linear term we can expand this thing 1 upon L plus delta x square, but we can't do it up to the first order, because for this problem this first order expansion is going to be insufficient. So we need to expand it to quadratic terms, and this is a difficult task, and I'm going to do it. I know that expanding the equation and using it to the first order, using it up to the first order, things are going to get difficult. We will get obviously bad results. So I'm going to expand it in powers of delta x to the quadratic terms, and to do so I'm going to write down it like 1 upon L square plus a delta x plus b delta x square. It can be written something like that. And so I'm going to write this equation further as 1 is approximately equal to 1 upon L. I need the term till delta x square, so I'm going to write down this 1 is approximately equal to 1 by L square, and there is no delta x square, so I can write it here 1 by L square multiplied by L square plus 2L delta x plus delta x square plus a delta x. And so I'm going to get only I need to take the values of delta x up to its quadratic value only, and that means I need to reach the power of delta x up to 2 only. So I'm going to write down it as a delta x, and I will take only this term so that it will become delta x square. I don't need any delta x cube, because any delta x cube is going to be 0 from here. I can only preserve terms up to quadratic value of delta x, quadratic power of delta x. Any power more than 2 will become 0. So I'm going to write down this as L square plus 2L delta x only plus B delta x square. So I'm going to take the first term only here, L square. And I can simplify these things. For 1 is approximately equal to 1 by L square, and 1 upon L square. So no, I would like to write it at delta x square. I am going to take the coefficient of delta x square, and I can write here coefficient of delta x square is here 1 by L square in this term. Here I can get 2AL plus 2AL, and here is BL square plus BL square, and I can now write the coefficient of delta x here, and so that it becomes in here 2 upon L in here, coefficient of delta x 2 upon L plus here AL square, and the only term left is 1 by L square multiplied by L square, that becomes 1. So the next thing you would like to write that delta x, take delta x common from both expressions, and you can write here delta x multiplied by 1 by L square plus 2AL plus BL square plus 2 upon L plus AL square is equal to 0. Since this relation must be satisfied for any small delta x, and if delta x is exactly not equal to 0 but close to 0, that means these two positive terms must be equal to 0. That you could write here simply as like 1 by L square, because two positive terms can be 0, then their sum is equal to 0, because nothing is negative here. So 1 by L square plus 2AL plus BL square must be 0, and separately 2 by L plus AL square must be equal to 0. And you can get here the values of A and B from here, and A is equal to minus 2 by L cube, and B is equal to 3 by L raised to 4. And put these values in this equation. 1 upon L plus delta x square is simply can be written as 1 by L square plus A delta x plus B delta x square. You got the values of A and B, and you can put all them together to get 2B square plus omega square L square equals omega square L raised to 4 1 by L square minus 2 delta x upon L cube plus 3 delta x square by L raised to 4 plus 2g delta x. And simplify it. You are going to get some 2b square plus omega square L square equals omega square L square plus 2g minus omega square L plus 3 omega square delta x square. And you can see here this g minus omega square L is also equal to 0, because we already found L equals G by omega square. What do you think? G minus L omega square is going to be 0, and this term is going to be 0, so that we can write here 2b square is equal to 3 omega square delta x square. So the square of the circular frequency of oscillation is determined. Now you can write here 2b square, or simply v square equals 3 by 2 omega square delta x square. If you differentiate it, you will get 2b dv by dt equals 3 by 2 omega square 2 delta x and d delta x by dt. Delta x assuming a length only, so you can write it here like dv by dt is basically that second derivative of delta x. Please keep it to dv by dt, and that will be equal to 3 by 2 omega square delta x, so that your angular frequency will become 3 by 2, square of angular velocity will be 3 by 2 omega square, so that this circular frequency will get under root 3 by 2 omega. Thank you very much for watching.